Good afternoon. This is Commander Nunez coming at you from the Challenger Center for Space Science Education in Alexandria, Virginia. And today we are privileged to have with us Miss Rebecca Mazzone. She's actually the Data Presentation and Visualization Manager for NASA's Constellation Program and Exploration Strategic Analysis Team at NASA's Kennedy Space Center. Throughout her career, Ms. Mazzone has been actively involved in simulation outreach, co-authoring several conference papers, and traveling within the U.S. and abroad to share NASA's advances and experiences with the modeling and simulation community. She holds a bachelor's degree in computer science and a master's degree in space systems, both from the Florida Institute of Technology. Without further ado, we will turn it over to Ms. Mazzone.
Thanks, Carlos, and hello everybody out there. It's really cool to be here with you today. As Carlos said, I'm at the Kennedy Space Center, and Kennedy is a really cool place to be because we get to see so many different aspects of what NASA does with its missions, from the launches and landings to even processing the hardware and working with the crew. So what I'm going to talk to you about today is actually some of the work that goes on behind all of that to go make our missions possible, specifically in the areas of modeling and simulation. So to get started, the first thing I want to do is give you a few basic definitions to make sure we're all kind of speaking the same language here. And the first thing we're going to look at is what a system actually is. Now, a system, simply defined, is a group of interacting, interrelated, or interdependent elements forming a complex whole. And, okay, I don't know what that means in English, so I'm going to try and explain that to you. Interacting is basically things that are working with each other. Interrelated means they're connected to each other, and interdependent means they need each other. Now, you use systems every day. Your computer system, your phone is kind of a system. If you have a gaming system at home, it's the same kind of thing. I have a Wii, and my Wii is awesome, and I pull it out of the box, and it's got a little Wii console, and it's got the little sensor bar, and it's got the little remote, and I put all of that together, and I stick a game in there, and hey, everything works. But if I take any part of that away, it's not going to work the same. So if I don't connect the sensor bar, then it's not going to read what I'm doing with the Wiimote. Or if I have all of the other pieces and the system's not there, I'm going to be swinging stuff around my living room, and it's going to wear me out, and I'm going to look pretty stupid, and it's not going to accomplish much. So the idea of a system is you have a whole bunch of parts that really need to come together to go make a thing do what it's supposed to do. If you look at the space shuttle is our national space transportation system, and that's why we launch STS-117 or 132 or whatever it is that's coming up, and it has three main systems. It has the orbiter, which is the big white part that everybody calls the shuttle. It has the external tank, which is the big orange thing, and it has the two solid rocket boosters on the outside of it. And all of those things come together, and we get this national space transportation system. Now, the thing that is challenging with systems is that you can have systems within systems. So on the shuttle, as you can see here, we've got a whole bunch of different things that we worry about, from the computer systems to the thermal protection, some of the wiring, the propulsion. And so for somebody who works shuttle, propulsion is kind of a subsystem. But if you're somebody who works propulsion, propulsion is the system. And so it can get kind of complex when you start layering these things. And then you can scale it up, and you can dock the station with the shuttle, and you've got another system there. So there are a lot of things that can go together to go make a system. And when we're doing this for space applications, this is kind of basically what a space system is. So that's kind of a basic definition on the system side. Hopefully I haven't lost you too much there. The other things that I want to make sure you guys understand first are modeling and what a model is. And a model represents the characteristics of something. So we have two ways that we can do this. The first way is physically, kind of like this little rocket guy here. And this is a model of the Saturn V that took people to the moon. And it looks like the real thing, but it's definitely not. But there's still things that we can learn about it, because we can look at it and see that we had to launch this whole thing, and this little piece up here is all that we got back. So it can give you some appreciation for the system that you're working with. One of the other ways that we'll go and model stuff is mathematically, and for some people this might not be as much fun, because this is where you take something like my big crazy propulsion book here, that has all of these equations and all of these properties for rocket engines and says, okay, when you go put these parameters into a model of how a rocket launches, this is the way that it should go behave. So we can model what something looks like, and we can model how something is going to go behave. Now, a simulation is when we actually go kind of push the play button, so to speak, on this model that we've put together. So we can take either just the mathematical models that we put a whole bunch of numbers into and push play and see what happens. We can take a bunch of different physical models and push play and see how they move and interact with each other, or we can do a combination of the whole thing. And that's basically the difference between a model and a simulation. Is the model is more the static thing, and the simulation is the action and what's actually moving around. One of the other terms that we talk about a lot with modeling and simulation is this thing called fidelity. And fidelity is just kind of a fancy way of saying how accurate is this thing that we're working with. So if you look at the two little Earths up on the slide, you can see that one is very detailed. The one on the bottom, that was an image taken by NASA that was put out there by Goddard. And then you've got this sort of cartoony adaptation above it that's much more low fidelity. And it really depends what we want to do as far as how much fidelity we need. So it's kind of like if we're talking and you say, hey, Beck, where do you live? And I go, oh, I live in Florida. If you're just talking and being nice and you actually live in Wisconsin somewhere, that's probably all you need to know. If you're trying to get directions to my house and all I tell you is I live in Florida, you're probably not going to be really happy with me, and you're going to be asking a few more questions. So that's where the fidelity concept comes in, is just how much detail do we need to have to do what it is that we need to do. So now that I've got the basic definitions out of the way, the question becomes, why does NASA use modeling and simulation? And at NASA, we tend to refer to modeling and simulation as M and S. We use a lot of acronyms out here, and M and S is one that I deal with every day. So with space systems, we have a number of challenges to working with them. The first is that they're kind of complex. They have a lot of parts and pieces. They interact with a lot of other parts and pieces, and there's a lot to them that you have to really understand and make sure that they're going to go work the right way. These are also very expensive and very large in most cases. So if we have to go replace something or if we go break something, that's kind of a problem. They don't really like spending money on things because we broke them, probably any more than your parents like when you break stuff. And so they're also large, so we can't pick up and move them around. I mean, imagine having to pick up and move your dresser 12 times before you knew where you wanted it to be in your room. It's really not an easy thing to go do. One of the other challenges we have with space systems is that we can't always test them on Earth. So we can try and pretend we know what to do in them, but some of what we do isn't going to work. For example, in gravity, the payload bay doors of the space shuttle will not open on their own. So when we're doing processing, we actually have to hook them up and have something open them for us because they don't work that way. The robotic arm on the space station is the same kind of thing. And there are also aspects of the environment in space that we can't always recreate here. So it's very challenging when you're building something to know how it's going to behave and how to go work with it when you can't fully test everything exactly as it's going to be when it runs. And one of the other challenges we run into is that sometimes we need to understand how to go work with these systems, but they don't exist yet. So we need to understand and plan for something that isn't there. And we can't see it, we can't touch it, but somehow, like here at Kennedy, we have to be able to go work with these pieces of the spacecraft when they show up, and we've never seen them before. And so that's also very challenging. So when we use modeling and simulation, it lets us understand what these systems are. We know what they look like. We know how to work with them. We have some expectation of what we're going to get. And by combining all of that in a simulated sort of environment, whether it's the way the numbers come out or the way the pieces fit together, we can go make better decisions about what we're doing and how we're going to do our work to make our mission happen. And the other thing it gets us is that we can go share